Hello everyone, just to repeat, my name is Pauley. I'm a PhD student at Wisconsin-Madison, and today I'm thrilled to be here to discuss our recent work in characterizing and deploying DScope, a cloud-native internet telescope. Every day, services deployed to the internet are subject to constant attack. Adversaries scan the entire IPv4 address space, ostensibly at random, searching for exploitable services and deploying exploits against those services. In that context, the security community has long looked for representative data on the behavior of these adversaries. And for the past 20 years, a key technique toward achieving this has been the internet telescope. Internet telescopes sit on routed but otherwise unused regions or footprints of IPv4 address space. And they receive but generally do not send traffic. The common intuition has been that when it comes to internet telescopes, the larger the footprint, the better. And this works under the assumption that internet scanning is random, because the larger the footprint, the more likely you are to see that random traffic. And so as a result of this, over the past 20 years, internet telescopes have led to myriad insights on botnets and other emergent threats. But as the structure of the internet changes and adversaries think about deployments and how better to exploit them, our measurement techniques also need to evolve. We've seen three structural changes in the internet in the past decade that frustrate existing measurement techniques. The first is the rise of public clouds. As high-value and vulnerable services consolidate on public cloud IP address ranges, adversaries can target these address ranges to see vulnerable services. The second is that the semantics of protocols and adversarial behavior are moving up the stack. Case in point, many protocols now sit on top of HTTP. And so, simply seeing network and transport level data like IPs and ports is not sufficient to understand adversarial intent. And third, adversaries are becoming more sophisticated and distributed. They can identify where telescopes and other detectors exist and avoid them, frustrating detection. Indeed, these hypothesized changes are not simply hypothetical. Our characterization of DScope that I'll be discussing, a telescope that is designed to work around these limitations, shows that DScope receives substantially higher coverage owing to its deployment. And so, in response to these structural changes, we set out to build an internet telescope for the modern internet, achieving three goals. Our first goal is to receive representative traffic that would be sent to real vulnerable services. And we do this by being deployed in situ on the same IP addresses that adversaries are targeting. We do this by deploying to public clouds. The second is that we want interactivity with clients and adversaries, both to collect application layer banner information and to elicit deeper adversarial response to the telescope. Finally, we want our telescope to be agile through the IP address space. The footprint needs to change over time to prevent characterization and avoidance by the adversaries. And so, in achieving these, we built DScope, a global, dynamic, interactive, cloud-based internet telescope. Now, that's a mouthful, so let's break that down by looking at how the architecture of DScope achieves our goals. Now, recall that we hypothesized that internet scanning is both random and targeted at cloud services. And so, to receive both of these traffic phenomena, we deployed DScope to a public cloud provider, in this case, Amazon Web Services, though we're in the process of expanding to many other providers. Within AWS, IP addresses that we allocate for the telescope are backed by actual compute in the form of EC2 instances. These instances complete TCP session establishment on all ports and receive, therefore, application layer banner traffic and elicit further behavior. These servers stay up for 10 minutes collecting data before shutting down. Keep that number in mind. This achieves interactivity. DScope is also a dynamic telescope. After releasing IP addresses back to the pool after 10 minutes, DScope allocates new IP addresses from Amazon's pool of 135 million IPs. And so, because IP address allocation is random, the footprint of DScope is continually changing, preventing adversarial characterization and yielding new coverage. And finally, DScope is global, deployed in 16 cloud regions worldwide. In effect, whereas traditional darknet telescopes sit on a single homogeneous range of IP addresses and do not respond to inbound traffic, DScope sits on a varied and ever-changing range of IP addresses that is in situ with services that adversaries are actually targeting, yielding improved coverage. Of course, DScope is not just a data collection platform, but also an analysis platform. After pcaps are collected, we perform real-time analysis in the form of fetching DNS records that cannot be retained later. And all of this is stored to Amazon S3. On a daily basis, we consolidate these into archival files for future analysis and sharing. For the purposes of the analysis in this paper, we were primarily interested in flow tuples. And so we perform a flow tuple extraction step and annotate those flows with geo-IP information and information on source networks. This enables the resulting analyses in this paper, where we compare it against existing telescopes and look at how cohorts of DScope affect coverage. And in a step that I think is one of the most important for open science, we're releasing the results of our paper as open data products from the research community to enable future science. Over the last 2 years of DScope being deployed on Amazon Web Services, we've collected data inbound on over 6.3 million Amazon IP addresses. And because Amazon has such a broad footprint acquired from many organizations over the years, these IP addresses span 110,000/24 IPv4 networks. This is more than any other telescope. As a result of our breadth and coverage, we receive traffic from over 15 million scanner IP addresses, providing broad coverage of adversarial behavior against cloud services and the internet at large. And best of all, we achieve relatively strong price performance with this. DScope is deployed every month at only a couple $100s a month, collecting data that will be invaluable to the research community. In the analysis of our work in the paper, we wanted to understand how DScope varied compared to traditional darknet telescopes. And so we selected 1 week of data collected by DScope and compared it with a week of data collected at the same time by a darknet telescope, Merit's Orion telescope. As a result, we came to 18 findings about cloud scanning on the internet and how best to deploy cloud telescopes. Well, that's a lot to cover in a 15-minute window. Today, I'll be focusing on 4 key findings that I think highlight the novel contributions of our work. First, let's talk about how the footprint of DScope achieves higher coverage. Now, we said that existing darknet telescopes work under the assumption that scanning is random, and we hypothesized that non-random scanning would lead to higher coverage for DScope. And so the question is internet scanning random? Well, we can actually phrase this as a hypothesis test that we can evaluate. Let's consider random scanning. An adversary who is random scanning has a given probability of hitting either the darknet, telescope, or DScope. And this is effectively a coin flip. Under the hypothesis of random scanning, this would be weighted by the size of the 2 telescopes in IPs. Now, to evaluate this, for a given scanner, we can look at the distribution, and we'll fill this in a second. We can look at the distribution of DScope IPs contacted by the scanner and darknet IPs contacted by the scanner. If scanning is random, we would expect a mass of scanners to occur about here in the histogram, weighted between the 2 telescopes based on their size. And in reality, we do see a mass of scanners in this region, saying that likely random scanning is relatively common. And this is not unexpected. However, perhaps more surprising is this mass of scanners here. These are scanners that contacted many DScope IPs, but few, if any, darknet IPs. And if we look at the expectation of this under the null hypothesis, we see that 450 times as many scanners are exclusive to DScope as we would expect under random scanning. And so what this all means is that there is a whole class of scanning behavior on the internet that is invisible to existing telescopes, and that DScope allows us to characterize that phenomenon. So we've seen how the footprint of DScope affects our coverage, but how does the interactivity improve our ability to monitor adversaries? Well, let's consider an example. Consider a botnet such as Mirai that's talking to servers and then reporting results to an adversary via command and control. It scans the internet randomly, and the darknet does not respond, so nothing happens. But DScope does respond to traffic. The botnet then reports this response to the command and control server, which then sends follow-on scans with real exploit payloads. It should be noted that this follow-on scan is what we're most interested in, because it is what reveals adversarial techniques and intent. So the question then is, does DScope see this follow-on scan behavior? To answer this, we can again phrase this as a hypothesis test based on the time series distribution of traffic from different scanners. When a botnet randomly scans the internet, when it contacts DScope will effectively be uniformly distributed over the time that we measure on that IP address, though not quite. We'll talk about that in a bit. However, in the case of the adversary must wait for a response from DScope, a message to the command and control server, before then sending follow-on traffic. And so, versus the expected botnet distribution of uniform, or rather a truncated exponential distribution, more info in the paper, the adversary will be delayed in time. And so by estimating the parameters of the time distributions of each adversary or each scanner, we can then determine using a KS goodness of fit test if adversaries reject the null hypothesis and perform delayed scanning. And indeed, we do see that this is prevalent behavior. Again, the blue line is expected behavior under our null hypothesis of random scanning. And the black series represents scanners that perform bulk scanning of DScope, however, were delayed in time, showing that they must be using information from other scanners such as botnets. And we explored this further in the paper and showed that that was indeed the case. So these must be responsive to the service activity of DScope. And so the takeaway here is that not only does the interactivity of DScope further elicit adversarial behavior, but our deployment model allows us to characterize that behavior statistically. Now, cloud telescopes do have a lot of advantages, but there are also challenges. Specifically, a key challenge that we faced in this work is that every cloud IP address is unique, both due to the history of when Amazon acquired those addresses, previously deployed services, and even latent configurations that still refer to those addresses and cause inbound traffic. Let's look at an example. In the paper, we wanted to understand if adversaries were performing geographic or regional targeting of cloud services. And so, in one example, we can compare the US1 region and EU2 region of Amazon Web Services. Now, looking at these two distributions of inbound traffic, we might initially think that the US1 region is being targeted geographically. In fact, this is what we initially thought. However, we performed a follow-on analysis, and thanks to the large number of IPs that DScope measures on, we were able to perform an analysis of how the year in which Amazon acquired an IP address affects traffic phenomenon. It turns out that IPs very recently acquired by Amazon Web Services receive substantially less scanner traffic than other IPs. And we hypothesize that this is because botnets are actually using outdated lists of cloud service IP addresses to target the cloud. When we account for this in the above distributions, differences between regions largely evaporate. And so, when performing analysis on cloud data, it's very important to account for confounding factors. But DScope's large IP address footprint allows for us to identify and mitigate these factors, achieving valid measurement. And so, we hold many IPs with DScope, but of course that comes at the cost of holding those IPs for only a short period of time. We pay per IP hour after all. And so the question is, how long should DScope hold IPs to achieve sufficient coverage? Here, we're interested in coverage of unique phenomena. Let's talk about source IP addresses contacting DScope as one of those phenomena. So we want to understand, as we measure for longer in an IP address, how does our coverage improve? Here is an empirical plot of our coverage of unique source IP addresses over the collection duration of DScope IP addresses. Now naturally, this increases over time. However, we also pay more money to measure for longer. And so our yield of phenomenon per dollar or per IP hour spent actually plateaus. And so this peak here is maximum price performance. We can fit a statistical model to the rate of new phenomenon seen on a given IP address, and extrapolating this out over time, we can also see when we achieve maximum coverage. And this occurs after just a few hours of collection. This broadly challenges conventional intuition in measurement, where we measure on individual IPs for a long time. We can also perform this on other phenomena, such as source ports, destination ports, networks, etc. And so DScope's deployment can be optimized for both of these cases, and even short collection durations achieve very high coverage and yield. So we've seen how DScope's footprint and interactivity allow new coverage. Its agility through the IP address space prevents characterization, and it has very impressive price performance. But what I think is one of the most important points of DScope is open data. Through DScope.org, we're making data products as a result of this analysis available to the research community to further science. And we're looking forward to the myriad insights about both cloud service security and general internet measurement security that will come from this. If you go to DScope.org today, you can also check out live daily updating visualizations that show not only extended results from our paper, but also information on real-time info of effectively internet weather against the cloud, current exploitation of deployed services. And if you're interested in more, you can go to dscope.org/sec23 for a director's cut of this talk, where we talk more about the benefits, challenges, and opportunities for cloud-based measurement. Thank you so much, and I'll be happy to take questions.